So the foundation of today's lesson, which involves solving polynomials using factoring, is to use the zero product property. The zero product property basically says that if you have two real numbers, A and B, and if you multiply them together and they equal 0, then either A must have been 0 to begin with, B must have been 0 to begin with, or both numbers were 0 to begin with, right? Because the only way you'll get a product of 0 is to have at least one of the factors be 0, okay? Why do we use the zero product property? We use it to solve polynomials, right? Or polynomial equations to find the zeros, roots, and x-intercepts, essentially what we would see on the graph. All right, so that is the value of the zero product property. It allows us to do that. All right, so let me kind of break down. It's a lot simpler than what it seems. If we move into example number 1, what you have is the product of two factors. The first factor is x plus 3. The next factor is 2x minus 5. The product of those two factors equals 0. So we get to use the zero product property, which tells us I need to split this into two equations. The first one is to take my first factor, which is x plus 3. I need to set that equal to 0. And then I also need to set my other factor, which is 2x minus 5. I need to set this factor equal to 0 as well. All right. What I would do next is I would solve both of them for x. All right. I would subtract 3 on one side, and we end up with x is equal to -3. Okay. So this would be considered my first root, or my first 0, or my first x-intercept, all right, of this polynomial. X equals -3. All right. So you guys know that an x-intercept means that that's where the graph will either touch or cross the x-axis, right? So if you're kind of painting this visual picture, that's what this number represents. At -3, the function will cross the x-axis, or it will at least touch the x-axis. And then we'd solve for the other x-intercept, which would be by adding 5 to both sides first. We get 2x equals 5, so we divide by 2. So x is equal to 5 over 2, or this could also be 2.5. Okay, so these are my x-intercepts. Now, the correct way to then be able to list x-intercepts is to list them as coordinates. So since this represents an intercept, the intercept would be -3, 0. And the other one would be 5 over 2, 0. All right, now, why do both of these values work? Well, if I, let's say, were to plug in -3 into my function, right, into x, right? By taking -3 and plugging it in into the first x value, -3 plus 3 becomes 0. And now I have 0 times whatever else would be in the next set of parentheses. Doesn't matter what it is, because 0 times anything becomes 0. Okay, so that's why, right, -3 counts as an x-intercept. The other potential x-intercept would be 5 over 2. This time, if I were to take 5 over 2 and plug it into both of my x values, if I plug it into this one, right, I would have 2 times 5 over 2 minus 5. This gives us 10 over 2, which is 5 again. So 5 minus 5 gives us 0, right? So then this would become 0 times anything is still 0. So either one of the values, -3 or 5 over 2, represent x-intercepts. Okay, so the process is fairly simple. Once the factors are multiplied together and they're set equal to 0, you basically split them into two equations where both of them are set equal to 0. And then you solve for x. Once you've solved for x, you write them as x-intercepts, okay, or as a coordinate, because this represents an x-intercept and this also represents an x-intercept. All right, depending on the book or depending on the teacher or instructor, there are various names. They could be called x-intercepts. They could be called roots. So if you ever ask, find the roots of the polynomial, they're basically asking you find the x-intercepts of the polynomial. If they ask you to find the zeros, that means the same thing as x-intercepts, right? Why do they call them zeros? It's because that's when the y-axis is 0, right? When you hit the x-axis, that's when the y value is a 0. So that's also why they call them zeros. Okay, so just know you got to switch between those 3 words, but they all mean the same thing. It just means find x-intercepts. Okay, so the answer would be both of these. All right, and so then in a future lesson, what we would do is we would take that information and we would start trying to build the graph of this polynomial with the information provided, which means we know that it's going to hit the x-axis at those 2 points. And then we just have to figure out the rest of the shape, right? So in this situation, if I were to FOIL out these factors, I could see that, hey, this ends up being a parabola. This is a quadratic. So that means I have a quadratic that crosses the x-axis it crosses the x-axis at -3 and at 5/2. And then from that, I could try to build the rest. Maybe try to find the vertex, all that good stuff. Okay. But in terms of algebraically, pretty simple. Right? What it means, it opens the book to a whole nother set of lessons. All right. Any questions there for number 1? Cool. All right, let's move on. In example 2, what I have now is the product of 3 factors. Okay, the zero product property still applies. If I have a times b times c equals 0, 3 numbers multiplied together and the answer is 0, that means either the first was 0, the second was 0, or the third was 0. So same idea, when they're already broken up into factors, your job is fairly simple. You're going to set it equal to 0, but you're going to have 3 different equations. All right. This one is always the trickiest one, right? Because you don't see it as a factor in parentheses, but that is if you think about it, like that's like a GCF that got factored out. We have to set that factor equal to 0. All right. So you just take it as 3x equals 0, and you're going to solve for x. Okay. The next one, we can see that this would be x plus 7 equals 0. And then the last one, 2x minus 9 equals 0. All right. Solving for the first one, 3x equals 0, is fairly simple. You're trying to get x by itself. So all you have to do is divide both sides by 3. So x ends up being 0. Okay. Let me not box that yet. All right. Next one, I have to solve for x, so I'm going to subtract 7. So x equals -7. And then for the last one, 2 steps, add 9 first. 2x equals 9, divide both sides by 2. So x equals 9/2, or this could also be 4.5. All right, so what does this tell me? This tells me that this has 3 x-intercepts, right? So this is not a quadratic. This has to be something else of a greater power. And if you were to FOIL all of this out, distribute all of the terms in, you would find that this gives you a cubic function, right? X to the power of 3, right? So we have 3 different roots, 3 different zeros, 3 different x-intercepts, okay? So if we write them all as x-intercepts, well, the first one would be 0, 0. The next would be -7, 0. And the last intercept would be 9/2, 0. Right, so these are all my x-intercepts. Any questions there for number 2? So hopefully it feels easy, right? All we're doing is breaking it up into 3 smaller equations. What's been nice so far is that it has been factored for us already. Most of the time, though, the polynomials will not be factored. It'll be up to you to factor them first and then solve for the intercepts. Okay, so that's where we move on to next in example number 3. All right, so let's move on. Let me change that to 3. Okay. So I have a series of steps here. All right. We have an unfactored polynomial now, right? We have a trinomial. Okay. I need to factor this first. Okay. Before I can then set my equations equal to 0. All right. Now you notice I wrote a note here. I circled the 2 and I wrote that this represents the number of solutions or the number of roots. All right. This is a x power of 2. That's a quadratic, right? So quadratics have a power of 2 for a reason, because it means that they have 2 roots, right? They have 2 roots. Later on, you'll learn that it could be either a real root or an imaginary root, complex root. There's a combination of roots out there, but they have 2 roots. All right, so at least 2 solutions. That's what we're looking for, right? So at the largest power, you see a power of 2, you need to end up with 2 solutions. Okay. So if you end up only with 1 solution, you know, you may have missed one. All right, so it says step 1 is to set equal to 0. This one is already set equal to 0. The reason I write that is because in other examples, sometimes it's not set equal to 0. So we want to make sure that like we've done that first. So it's just kind of like a confirm. Is it equal to 0? Yes, it is. Okay, now we can go into the factoring process. All right, so I feel like this one is fairly simple, right? I'm not going to go into the whole Xbox method. I feel like this one could be done with a little bit more traditional method. I know that I need to get x squared, factor that. So I know that that's x times x. What factors would multiply to be -9, but add up to be -8? The reason why the 0 has a line through it is so that you don't confuse it with an O. All right, so we're factoring what values, what factors multiply to be -9, but add up to be -8. Nine and -1 would add up to be +8. I want them to add up to be -8. There you go. Right, so we want -9 and +1. Okay. So we factor the polynomial or the quadratic, we factor the quadratic, and it's still set equal to 0. When it's set equal to 0, now we can see, hey, this is where 0 product property can be applied, because I have a factor times another factor, it equals 0. So now I can split. All right, so we split, and we have x minus 9 equal to 0, x plus 1 equal to 0. These are pretty easy to solve, right? We just add 9 to both sides. X equals 9. That'll be the location for one of the intercepts. Subtract 1. X equals -1. Okay, remember that these are intercepts. Okay, so a lot of times I get students who just box the answers, they just box the X. This needs to be written as an intercept. So 9, 0 and -1, 0. Any questions for number 3? So notice how that power indicated I needed 2 solutions. I found 2 solutions. If it would have been a power of 3, I would be looking for 3 solutions. If it was power of 4, I would be looking for 4 solutions. Right? So the largest power I see in the polynomial indicates how many roots or solutions or x-intercepts I should have. All right, so far so good. All right, let's move on. All right, we get to number 4 here. First part is, or at least part 0, is double check that your polynomial is set equal to 0. If it is, then you're good. We get to just move on to the factoring part. Okay, So what do you think we should factor first? Take a look at the polynomial. Tell me what you think or where you think we should start. Okay, you identified GCF, right? Okay, I do too. So we can start there. Definitely want to start there. What is the GCF that you find between the three terms? Yeah, 2x. Okay, I like it. So we're going to go ahead and factor out a 2x. All terms share x. They can be divided by x, and they can all at least be divided by 2. So we have 2x times the rest. All right. In this case, we end up with 3x squared minus 8x plus 5. And then this is still equal to 0. Do I want to split at this point, or is there something else we ought to try? Probably not a good idea to split right now. Okay, why is that? Okay, what about that trinomial though? What should we be looking to do before we move into that step where we set them equal to 0? Am I done factoring is what I'm trying to ask. Yeah, we're not done factoring. Okay, you have a trinomial. You need to attempt to factor this trinomial because most of the time it'll be factorable. Okay, so in this particular case, we can do a little bit of work on the side. We can do a little Xbox method, make sure that this gets factored out completely. Okay, or you can jump in and do a traditional method as well. So let's just go ahead and see what this gives us. With an Xbox method, right, we draw out our X. We know that we would be multiplying the first term and the last term. That gives us 15x squared. But the sum has to add up to be negative 8x. What are those factors that would satisfy the product of 15x squared, but the sum of 8x? Yeah, a negative 5x and a negative 3x, right? The product becomes positive, the sum is still negative. So we then move on to the box. Remember that the two terms that we use on the sides of the x get moved into the diagonal in our box. So negative 5x and negative 3x. Okay. Now, what term am I going to use in the first box and in the last box? No, I don't reuse negative 8x. Yeah, we look at the polynomial, the leading term and the final term, right? Usually it's a constant, but the leading term and the constant. All right, so 3x squared and positive 5. All right, common mistake. Students will go back and select this term and this term. Why would it be incorrect to select those two terms to place them into your box? Why would it be incorrect to, not necessarily because they're not factorable, it's because, yeah, we already divided them using the GCF. So our new trinomial, the one we're working with, is the one that's inside the parentheses, right? So this is what we need to use, not the ones from above. Okay. All right, so now we still need to do the GCF here on the box 4 times, 2 times for the rows, 2 times for the columns. So let's go ahead and do the top row, 3x squared minus 5x. What is the GCF between the two terms? Yeah, just x, Okay, what about the second row, negative 3x and positive 5? Yeah, there's not really a well, there is a GCF of 3 and 5, it's just 1, but because the leading term is negative, we factor out negative 1. All right, what about the first column, 3x squared minus 3x? What is the GCF between the two terms? Yeah, we can divide both by 3. They both have x in common, so 3x. And then finally, negative 5x and positive 5. What's the GCF? Yeah, we want negative 5. All right, so now I have my new factors, right? So you see how I can't just stop after a GCF. I need to then look to factor the trinomial. This is what we call factor completely. Every time you factor, the assumption is we're asking you to factor completely, right? You find a GCF, that's great, but there's more pieces, most likely, 90% of the time, there's more pieces for you to continue to factor down. So now we have a completed set of factors because we know that this polynomial, the trinomial, factors into 3x minus 5 times x minus 1. And what additional factor must be brought down to be a complete part? Yeah, the 2x, right? Don't forget this part. Okay. So notice, what was the leading power at the very beginning? Power of 3, right? That means you should arrive at 3 different solutions. So I have at least 3 factors. Looks like I will get those 3 different solutions. The first one here, 2x. This is always the awkward one, but you literally just write 2x and it's equal to 0, okay? And that's what you're gonna solve. The next one, 3x minus 5 equal to 0. And the last one, x minus 1 equal to 0. Okay. So now we solve for the 3 roots or zeros or x-intercepts. So let's go ahead here. To solve 2x equals 0, you need to divide by 2. So 0 divided by 2 is still 0. Next one, we would add 5 to both sides. 3x equal to 5. Divide both sides by 3. So x equals 5 over 3. And then finally, just add 1. So a lot of these, right, quick mental math, and you can finish them up. So now we have 3 x-intercepts, 0, 0, 5 over 3, 0, and 1, 0. All right, these are my intercepts. Any questions there for example number 4? Okay. Example number 5. All right. So a couple things before we begin. Largest power that you see. That's a 3, right? So we should eventually arrive at 3 solutions. Okay. All right. It's already set equal to 0. So that means we can begin the factoring process. So now I want you to go ahead and take a look. Where would you begin? Where should we begin? Okay, yeah, we have a GCF, right? Both terms have x in common. So I'm glad you went with that approach instead of trying to force it into a sum or difference of cubes, right? A lot of times you see the x to the third and you think, okay, it's got to be sum or difference of cubes. It's actually just a GCF. So factor out the x from both terms. And now we have x times x to the third divided by x gives us x squared. And 25x over x is just 25. Okay, this is still equal to 0. What do we know about x squared minus 25? What do we call this type of polynomial? A difference of squares. Very good, right? So we know how these factors are fairly simple. X squared is perfect. This is just x times x. 25 is perfect. That's 5 times 5. It's also a difference, right? So this is the one that can be factored. So we know that this factors into x minus 5, x plus 5 equal to 0. And then I cannot forget to bring down that GCF. If I don't bring down the GCF, I'm only going to end up with 2 solutions. And I'll probably ask you, there was supposed to be 3 solutions. Where's this third one? So it's so important to bring down that GCF. All right. So once again, 3 solutions. The first one will be awkward. You're going to feel like there's something missing because you didn't really solve for anything. But this right here is a factor. So you set the factor equal to 0, but the factor is pretty much the answer. That's it. There's nothing else you can do. X equals 0. That's it. Nothing to solve for. All right. So that means you have an intercept at 0, right, on the x-axis. So that's good. You're done. The next one, x minus 5 equals 0. The last one, x plus 5 equals 0. All right. So you see what I mean about, okay, x minus 5 equals 0. That feels like you're doing something okay because, okay, I'm going to solve for x. You actually do a step. Plus 5, plus 5. So x equals 5. Same thing for the other one, right? You subtract 5 from both sides, you're going to get x equals negative 5. This is the one here that always trips students up because they felt like they didn't solve for anything, right? And they feel like it's not correct to just set it equal to 0. I'm telling you that it is, and it happens often where you just have a GCF out front, bring it down, set it equal to 0, and sometimes it's just going to be x equals 0, and that's it. There's nothing else you need to do. All right. You don't divide by 0 on both sides. I've seen a lot of weird things. You don't divide by x on both sides. Like that's it. Your goal is, what is x? X is 0. Okay, I'm done. So now my 3 intercepts. What are my 3 intercepts? Write them out as coordinates. So 0, 0 is the first x-intercept. The next one would be 5, 0. The last one will be negative 5, 0. All right, so we have a cubic polynomial crossing through the x-axis in 3 different locations. Okay, any questions there? All right, let's move on. Number 6, I'm going to put a star next to it. This one is a double. It's a special case. Okay, you'll see why. All right, so quick checklist. I'll definitely let you try one on your own after we get through number 6, just because it's a double case. It's a special case, so I want you to know that this is a possibility. All right, so let's kind of just do a quick check to make sure things are in order. First of all, it's set equal to 0. That's good. And then also I can identify how many solutions I will need. It's 2, right? Power of 2 is the largest power. I need 2 solutions, 2 intercepts. So let's go ahead and try to factor. Okay. Was there a GCF for us to factor out? No, right? So then we jump right into just factoring trinomial. You can do your Xbox method. This one, you can use a traditional method because there is no leading coefficient, right? So we know that in order to get x squared, it's just x times x. And now you're trying to find factors that multiply to be positive 16, but add up to be negative 8. What are those factors? Yeah, negative 4 and negative 4. All right, so negative 4 and negative 4. And this is set equal to 0. Okay, now notice something. That gives us x minus 4 equal to 0. This one also gives us x minus 4 equal to 0. Okay, so when we solve for both of them, this is going to be 4. This is also going to be 4. And you might be wondering, aren't I supposed to get 2 different solutions? Well, sometimes you get something called a double root, which means that the root happens twice. And that's okay. That still satisfies the fact that you need two intercepts, but it's just one intercept counting as a double root. All right. So whenever you have the same intercept or the same solution twice, it counts as a double root. So this is one of those special cases where we have an intercept at 4 comma 0, and then I always label it with a dr. Okay, the dr represents a double root. Okay, and we'll discuss what a double root means on a graph, but basically a double root is a place where it'll touch the x-axis at that point, and then it bounces back. Okay, it'll bounce back. It won't cross the x-axis. Okay, here's a reason why. Here's another way for you to look at this. X minus 4 times x minus 4 could also be written as x minus 4 squared. Right, think of a function. What's the vertex of this function right here? Bragging rights if you can remember what the vertex is for that quadratic equation right there. And I know it's been a while, but I hope you remember. You're looking for h and k. What's your h? What's your k? No, it would not be 0, 0. I have an h value. It's there. It's inside my parentheses. I'll give you another hint. Opposite keep. There you go, right? So what's my vertex? It's 4, 0. What do you know about the vertex? That's either the lowest point or the highest point on a parabola, right? So you can imagine this as a parabola with a vertex at 4, right? So the vertex is at 4. Well, that's the very bottom of the parabola. That means it's not going to continue downward. That's where it's going to bounce and then go back up. So it creates that bounce point on the parabola, right? That's why, right, the double root gives that effect. A lot of times you can see it also as like, oh, that's also my vertex. A lot of times, right, it shows up as both. So that's the kind of stuff we'll get into, next week probably. Okay. All right. Any questions? So special case, right? There will be times where you will arrive with a intercept that is the same answer twice. Those are known as double roots. All right, so I'm gonna take a little break. I'm gonna give you guys a chance to practice here, okay? Follow my hint, all right? Set the polynomial equal to 0 first. Okay, so see if you can get through this one. I'll give you a few minutes and then we'll check back and we'll review answers. All right, so let's check back in here. This should have been your first step on this problem. The zero product property does not work if it's not equal to 0 first. So if you attempted to, I'm not sure what you may have tried, but if you try to do anything else but this first step, then you're kind of moving in the wrong direction. So you want to add 7x so that you have all the terms on one side of the equation and it's set equal to 0. Then we look to factor. All right, so in this situation, I don't have a GCF, so I just have to do a traditional or an Xbox method. I can see here that my factors, they're fairly simple because it's a plus plus first of all, so it's plus plus. And then on top of that, the only factors for 3 are 3 and 1, so that's 3x and x. And the only factors are 1 and 2 for positive 2. So I just have to make sure they're in the right place because they have to add up to 7x. So I know that that's probably going to be a 2 here and a 1 here. Okay, so a quick smiley face check. Hey, that's 1x. 3 times 2, that's 6x. So hey, that adds up to be 7x. That means I'm good. That means that these are the correct factors. So now I move on to that last process of solving, right? I'm supposed to end up with 2 solutions because the power of 2 tells me how many roots I will find. So we split 3x plus 1 equals 0 and x plus 2 equals 0. So now we solve. All right, we subtract 1, 3x equal to -1, and divide both sides by 3. So x equals -1/3. Other intercept, subtract 2, x equals -2. So my 2x intercept should be listed as -1/3, 0, and -2, 0. All right. How many of us were able to get those 2x intercepts? Any questions on number 7? All right, cool. Right, so that's one of the variations you'll see. Definitely be on the lookout for that. You want to have a polynomial equal to 0 first. Okay. Similarly here for number 8, right? We have polynomial on the left side, but it's equal to a constant on the right side that's not 0. So that ought to be our first step, right? We want to add 7 to both sides to give us a new polynomial of 7r squared minus 14r plus 7 equal to 0. Okay. I want to look to factor. Is there something here that they all have in common? They have 7 in common, but not 7r. The last term is just a positive 7. It doesn't have a variable. So we can factor out a 7. That gives us 7 times r squared minus 2r plus 1 equal to 0. Okay, now I want to talk about something here. 7 is just a constant. There is no variable there. Another hint is that we only ought to end up with 2 solutions, okay? So one of the issues that students tend to run into is, am I gonna have to set 7 equal to 0? Well, if you do, you're not solving for anything, and you're also creating a statement that's not true. So how do you eliminate this kind of confusing part about 7? Well, remember that this is 7 times the rest of the polynomial, and you can easily just divide both sides by 7 to get rid of the 7. Okay, so I'm going to do that because that helps towards the end, not have to worry about what happens to the 7. 7 divided by 7 on the left side divides out, becomes 1, aka cancels. So at least what it does now is it just simplifies things for me, and it just leaves me with the polynomial of r squared minus 2r plus 1 equal to 0 divided by 7 is still 0. So when I end up factoring this r squared minus 2r plus 1, I don't have to worry about the 7 anymore. The 7 was not going to give me an additional solution. I didn't eliminate a solution. 7 was just a constant that got factored out. Okay. It's different when you factor out a variable because the variable holds a spot for a solution, but the constant does not. Okay, so we can just divide both sides by 7, get rid of it, and now we can just focus on finding the 2 solutions that are part of this polynomial. All right, so let's go ahead and factor. We divided by 7. So it's the same thing. It's the same thing as if we would have had like 7 times x equals 0. You divide both sides by a 7. That's the idea, right? That's the idea. We're trying to get rid of the 7 because I know later on, the common confusion that tends to happen on a problem like this is that students will say, here's a solution, 7 equals 0. That's not a solution. That's a statement. That's a false statement because 7 does not equal 0. So I'm trying to avoid us getting to that point and having to wonder, what do I do with this 7? We just divide it from both sides of the equation, and now it's gone. So now we can just focus on this part. All right, so let's factor. Simple one here. In order to get r squared, that's just r times r. I need the product of two numbers to multiply to be -1 and add up to be -2. What could those factors be? Yeah, we want -1 times -1. The product of -1 times -1 is +1, but -1 plus another -1 gives us -2. So this gives us r minus 1 times r minus 1. All right. Once again, this is a double root situation because you can see how this, when I split it, I'm going to get the same solution. So rather than doing it twice, I'm just going to do it once. R equals 1, and I'm going to call this a dr. Okay, that's a double root. So then I have my intercept as 1, 0. Okay. Any questions there for number 8? All right. And then let's move on. All right. So for the sake of time, I'm going to move to number 10. Number 9 is very similar to some of the other problems. You kind of distribute and then you move your terms over. So I will leave this one for you to attempt on your own. And we can review it quickly on Thursday, right before the quiz. I want to show you number 10 because that one is a little bit more important. All right. Number 10 here. Question on 9, yes. Doesn't matter which side we move. Typically, it's traditional to have all your terms on the right side, but not necessarily, no. No, as long as you distribute everything and then you move all the terms together onto one side, then you can factor and so on. Okay, so number 9 is kind of doable, just distribute, move your parts. Let's get to number 10 here. All right, so number 10, why do I want this one? It's a grouping problem, right? We've done factoring, right? And I want to now try to do a factor by grouping and then also solve for the roots, okay? So taking a look at this polynomial, first thing I notice, hey, that's a power of 3. So I'm looking to find 3 solutions to this problem, or 3 x-intercepts. When it comes to grouping, right, the first thing we do typically is split the terms down the middle, right? Hoping that the first 2 terms will have a common factor and the last 2 terms will have a common factor. Let's go ahead and attempt it. First 2 terms, what GCF do we have between 10y to the third and 25y squared? 5y, just 5y? What's the lowest power they both share? Yeah, 5y squared. So definitely want 5y squared factored out of both of these. All right, and that leaves us with 2y plus 5. Okay. All right, now let's take a look at the next 2 terms. 8y plus 20, what do they both have in common there? They can both be divided by 2, but there's something bigger. Yeah, they can both be divided by 4. So that means we want to factor out a positive 4. We divide by 4 here to both terms. And that should give us 2y plus 5. Okay, and this is still all equal to 0. How do we know we're on the right track? That we're on the right track when it comes to grouping? Yeah, the inside of those parentheses are equal, right? So that tells us that there's still one more GCF left to be pulled out of this. All right, so that new GCF is 2y plus 5, right? That's what they both have in common. So when we do this one more time, it becomes 2y plus 5. And the leftovers, right? We have leftovers, 5y squared and positive 4. They become the terms of the other factor. All right, and this is still equal to 0. Okay, so we're going to attempt to solve this. Now, there's a factor here, 5y squared plus 4. I can't really do much with that. So I'm going to have to solve for y using a different method because I can't factor this, right? 5 is not a perfect. And even if it was, that would be a sum of squares. So there's really no way to factor this right now. All right, but we're going to attempt to break it up into those two equations anyway and see what we can do. There is a way to solve, and you'll see. So the first one is 2y plus 5, and this is equal to 0. The next one is going to be 5y squared plus 4 equal to 0. So let's find our first root. First root, subtract 5 from both sides. 2y equal to negative 5. Divide both sides by 2. And y is equal to negative 5 over 2. Okay, so I found one root. Now let's take a look at the next one. All right, this one you might remember how to do something like this when we were doing solving for intercepts of a quadratic. All right, let me walk you through. Hopefully you remember. We're trying to get y by itself, but I can't factor any of this. So I have to try to use like solving with the square root method. So the first thing I need to do is move the 4 over, move the constant. So I subtract 4. 5y squared is equal to negative 4. Need to get y by itself. So I divide both sides by 5. So now I have y squared is equal to negative 4 over 5. What do I need to apply in order to get y by itself? Yeah, we need to apply the square root. Y squared taken to the square root, that leaves us just with y. Now here's something I hope you guys remember. If I take the square root, I basically generate a positive and a negative of that value. So it's the plus or minus of the square root of negative 4 over 5. Okay. So look, I technically have my 3 roots. Here's one. Positive root negative 4 over 5 is another root. And negative square root of negative 4 over 5 is another root. So here's 1, here's 2, here's 3. However, what do you notice about the inside of that square root? There's a negative in there, right? And when we have negatives inside of the square roots, what kind of numbers do they become? Yeah, they become imaginary. So this particular polynomial, it has 3 roots. One of them is real, 2 of them are imaginary, but it still has 3. Okay, and we're going to get into a lot more detail about this when we get to like unit 6, where we're going to spend a lot of time with imaginary numbers. Okay, but these are still valid solutions. Okay, however, it's just that these are imaginary. So this one would give me a real root, right? This is a real x-intercept. And these are imaginary x-intercepts, which means that they don't show up on the graph. Yeah. So imaginary, we would have, I'm just going to write it as like this, just to keep it short and in the interest of time. Right, I have both of them are there, they're accounted for, right? But I would have those two intercepts, the positive and the negative. But there are my three roots, okay? And there it is for number 10.